In today's lecture, we are going to look at the issue of the covariance of Dirac's equation. After all, the whole point of this exercise in deriving the Dirac equation was to find an equation which is consistent with the special theory of relativity. In particular, the basic demand of the special theory of relativity that the laws of physics be the same for all inertial observers. Let me just quickly remind you of what the Lorentz transformations are. When you consider two inertial observers, let's label them O and O prime, so they are in different inertial frames, they will describe the same physical event by ascribing space-time coordinates to those events, but of course, because they are different observers, their space-time coordinates would differ. The space-time coordinates as measured by the observer O will be denoted by x mu, where mu, the Greek index, runs from 0 to 3. x0 stands for c times t. x1, x2 and x3 are x, y and z, the spatial coordinates respectively. And the Lorentz transformation essentially relates x prime mu, the space-time coordinates as measured by observer O prime, to x nu, the coordinates as measured by the observer O. And what we demand is x prime mu is lambda mu nu x nu, where we actually have a sum over all values of nu. So this really is lambda mu 0 x0 plus lambda mu 1 x1 plus lambda mu 2 x2 plus lambda mu 3 x3. What we are doing is we are using what should be familiar by now, the Einstein summation convention, where an index is summed over if it is repeated. Moreover, because we are dealing with non-orthogonal transformations here, the Lorentz transformations, we have to distinguish between vector components and covector components. Coordinates are the prototype for vector components and they transform by this coefficient matrix lambda, whose elements are the lambda mu nu. We write lambda with an upper mu and a lower nu, that is, we write the indices from top left to bottom right to indicate that we are talking about the actual coordinate transformation coefficients. I hope this particular notation is not unfamiliar to you. If it is, you can take a look at some of the videos I had made on tensor analysis where I describe clearly the rationale behind this. Anyway, assuming that you understand why the notation is like this, let's go ahead and talk about some properties of these Lorentz transformation coefficients. One basic demand which you have is that the interval eta mu nu x nu should be invariant. That is, two observers who might very well disagree about the values of space-time coordinates would agree about what this particular quantity, the so-called interval, is. And that immediately gives rise to a restriction on the possible coefficients of a Lorentz transformation. It must obey the relationship eta mu nu lambda upper mu lower rho lambda upper nu lower sigma equals eta rho sigma. I am pretty sure all of you are familiar with the idea of raising or lowering an index, that the eta lower mu nu can lower indices eta upper mu nu, which are actually inverses of eta, raises indices. The eta here is nothing but the diagonal matrix with elements plus 1, minus 1, minus 1, minus 1. And using this raising or lowering of indices, we can actually write another relationship which is exactly equivalent to what I have written down here, which is lambda lower nu upper rho lambda upper nu lower sigma is delta rho sigma. Just in case you are not very familiar with what is going on here, let me point out that the eta mu nu sitting on the left of lambda mu rho would lower the index mu and convert it to mu. So you get lambda nu rho with both nu and rho sitting downstairs. But that's not a very useful quantity to talk about. So what we do is, in addition to lowering nu, we raise the index rho. Of course, that will raise the index rho on the other side as well. So, in order to do that, what you need to do is apply the inverse matrix, eta inverse on eta, and that will actually change the eta to a delta. So you get delta rho sigma. In case these things are not familiar to you, please look it up, or you can take a look at my tensor analysis videos where these are described in some great detail. One immediate consequence of this relationship is that the determinant of the matrix lambda has to be equal to plus or minus 1, and we are going to make use of this result later. Now our aim is, as I said, to show that the Dirac equation retains its form when I go from one inertial observer to another inertial observer. That is, the Dirac equation is consistent with the principle of relativity. Now, in the Dirac equation, you have spatial and temporal derivatives with respect to the delta x moves. And we know how they transform when you transform your coordinate system. However, there is another quantity in the Dirac equation which is psi. And we need to know, in order to establish this result, how does psi actually transform when you change from one inertial frame to another. Most of today's lecture will be devoted to finding this particular transformation rule for psi, which, let me remind you, is not a single function, but rather a collection of 4 wave functions in a column vector, or as you can say, a column vector valued function. Now, before we do that, it would be useful to recast the Dirac equation in a slightly more relativistic form, so that some of the considerations that we will make become easier to do. Why is this form not relativistic as it stands? Well, these coefficients that we have put in, the coefficient 4x4 matrices, alpha I and beta, let's take a look at where they are. The alpha i's multiply spatial derivatives. The beta multiplies just the energy term, mc square, rest energy term mc square psi. There is no coefficient on the del t term, and that actually makes it look slightly not so relativistic. Of course, this does not mean that this equation is not consistent with special theory of relativity. It just does not look all that relativistic, simply because, in a sense, time has a special different role than the spatial derivatives. How do we handle that? Well, it's a very simple matter to move the matrix beta from the rest energy term to the time derivative term. Remember, beta is a matrix with the property that beta square is identity. So if you multiply this equation from the left by beta, you are simply going to get the beta on the del t, and you are going to have no beta in the rest energy term. So basically, what we do is change the notation a bit. Because we are multiplying the Dirac equation on the left by beta, we are going to introduce the new set of matrices called the gamma matrices, or the Dirac gamma matrices, where gamma 0 is beta, and gamma 1, gamma 2, gamma 3 are simply beta times alpha 1, alpha 2, alpha 3. Now the reason why we do that is the following. If you were to multiply the Dirac equation by beta on the left hand side, as we said, what you are going to get is IH cross beta del psi del t. I have divided through by c, so that we get 1 by c del psi del t. Remember, x0 is ct. So 1 by c del psi del t is del psi del x0. On the other side, we have minus IH cross times beta alpha I del xi psi plus beta square mc psi, which of course is just mc psi. If we move everything to one side now, note that what we are going to get is IH cross times beta times 1 by c del psi del t, which now becomes gamma 0 del psi del x0. And the beta alpha I del xi psi, which has moved to the left hand side now, simply becomes gamma I del psi del xi, and you have a minus mc psi, which comes from the beta square mc psi. What is very important is gamma 0 del psi del x0 plus gamma I del psi del xi is exactly the right form for what looks like a scalar product in standard special relativity, where you have something with an upper index multiplying something with a lower index, and the index is repeated, so you sum up over it. As we will see later, this really is not quite correct. What we are getting, of course, is not really a scalar, but at least notation-wise, this looks a lot better, a lot more relativistic than our earlier notation, which treated spatial derivatives and time derivatives on slightly different footing. Of course, just by making it look more relativistic does not make it really relativistic, so we still have a lot of work to do to show that this is relativistically covariant. This does bring me to a rather important and nice notation. Combinations like these, gamma mu, a mu, where gamma mu's are of course the 4 gamma matrices, and a mu are the components of a covector, is quite common. This is very useful in relativistic quantum mechanics, and because this occurs very often, there is a standard notation for this. It's simply A, the kernel letter for the covector, with a slash. Using this notation, gamma mu del mu is often shortened to del slash. This is called the Feynman slash notation. And we will make extensive use of this in later lectures. In today's lecture, I will refrain from using this. I will just use the expanded IH cross gamma mu del mu psi minus mc psi equals 0 form for the Dirac equation. Now, before we go any further, let us take a look at some of the details of this gamma matrices. They are, of course, things which we have derived from using the beta and the alpha, and their properties can, of course, be found out from the properties that we already know of the beta and alpha matrices. First, an explicit form. We have already seen an explicit form for the beta and the alpha matrices in the Dirac representation, where beta was this diagonal matrix with 1, 1, minus 1, minus 1 down the diagonal, written in 2 by 2 block form as identity sitting on the top corner and minus identity on the bottom corner, and of course zeros everywhere else. And the alpha i's, the 3 alpha matrices, were also 4 by 4 matrices, written in this 2 by 2 block form as 0, sigma I, 0. Let me stress that this is just one set of matrices which satisfy the Dirac conditions. It is very easy to see that any set which is related to this one by a similarity transformation, and if you want to maintain Hermitianity as well, by a unitary transformation, will also satisfy the same anti-commutation relations as beta and alpha I do. So they have just an equal status as far as this is concerned. So this is a particular representation that we are looking at. In other representations, these matrices will look different. It is very easy to carry out the multiplication gamma I equal to beta alpha I to arrive at the forms for gamma 0 and gamma 1, gamma 2, gamma 3 in the Dirac representation. Gamma 0 of course is the same as beta, and gamma I, which is beta alpha I, can be easily seen to be this following matrix. It's again a 2 by 2 block matrix with 0 and sigma I on the top row. 0 of course is a 2 by 2 0 matrix, and minus sigma I 0 in the bottom row. Once again, let me stress that any set of 4 matrices which are related to these by unitary transformations will also work as gamma matrices. What we will see later is that all gamma matrices, all matrices which satisfy the basic demand of the Dirac conditions, will actually be equivalent to each other in this sense that one set can be found by carrying out a similarity transformation on the other set. Now, what we need to do now is re-express the Dirac conditions which were in terms of the beta and the alpha matrices in the language of the gamma matrices. Because from this point on, we are going to focus primarily on the gamma matrices and forget about the beta and the alpha matrices. So, the Dirac conditions in terms of the beta and the alpha, where beta squared equals identity, of course 4x4 identity, because these are 4x4 matrices. Alpha I beta plus beta alpha I equals 0. That is, alpha I is anti-commute with beta for each of the i's. And for any pair of indices I and j, the anti-commutator of alpha I and alpha j is twice delta ij times the identity matrix. Now let us try to recast each and every one of these in the language of the gamma matrices. The first one is of course rather trivial. Since beta is equal to gamma 0, beta square equals I4 simply becomes gamma 0 square equals I4, which can easily rewrite as gamma 0's anti-commutator with gamma 0 is twice I4. Now, what about the next one? Alpha I beta plus beta alpha I equals 0 can be easily rewritten in terms of the gamma matrices by multiplying the whole equation on the left by beta. So you get beta alpha I times beta plus beta square alpha I. And now, beta times alpha I beta can be rewritten using the associativity of matrix product as beta alpha I times beta, and the beta square alpha I can be rewritten as beta times beta alpha I. So this immediately translates to gamma I times gamma 0 plus gamma 0 times gamma I equals 0. That is, gamma 0 and gamma I anti-commute. Finally, we come to the last equation. Alpha I alpha j plus alpha j alpha I is twice delta ij I4. Now we want to change both the alphas to gammas, and for that we need two beta matrices. Now one quick way of doing that would be to multiply on the left by beta square, which remember is the identity. So the right hand side does not change at all. But beta square alpha I alpha j is not what we want. We want beta alpha I times beta alpha j. For that, what we need to do is move one beta through alpha I, and because betas and alpha i's come anti-commute, you're going to incur a minus sign. So this becomes minus beta times alpha I beta. One of the two betas have been moved across the alpha I times alpha j. And similarly, on the other term, you will get minus beta times alpha j beta times alpha I. That is the left hand side. The right hand side, of course, is twice delta ij I4. Now, you can, of course, rewrite this as gamma I times gamma j, the first term. Of course, there's a minus sign which we move to the other side. Remember, all we are really using once again is just the associativity of the matrix product. So, gamma I gamma j plus gamma j gamma I equals minus twice delta ij I4. So, what we have is one more anti-commutator relation. Gamma I anti-commutator with gamma j is minus twice delta ij I4. It should be pretty easy to see that we can put together all these anti-commutation relations. Those with gamma 0 with itself, gamma 0 with the gamma i's, and the gamma i's with gamma j's into a single anti-commutation relation between gamma mu and gamma nu. Let me remind you once again, mu runs from 0 to 3, whereas I runs only from 1 to 3. And putting them all together, you simply get the anti-commutation relation. Gamma mu nu plus gamma mu is twice eta mu nu I4. Let me just remind you, eta upper mu nu are the components of the inverse of the eta matrix, but eta is self-inverse. So numerically the components are the same. They are plus 1 for 0, 0 and minus 1 for 1, 1, 2, 2 and 3, 3. 0 for all other cases. And it's very easy to see that this is exactly what those three anti-commutation relations were saying. So one more advantage of using the gamma notation is not only does it make the Dirac equation look sleeker and more relativistic, the anti-commutation relation also becomes more compact. You can write one single anti-commutation relation Gamma mu's anti-commutator with gamma nu is twice eta mu nu times the 4x4 identity matrix. Another property of the gamma matrices, which will be useful in later lectures, is a discussion of their Hermitianity or otherwise. Remember, the beta and the alpha matrices were each Hermitian. What about the gamma matrices? Let's take a look. Gamma 0's adjoint is of course beta's adjoint, and beta's adjoint is beta, so that's gamma 0. So gamma 0 is Hermitian. What about gamma 1, gamma 2, gamma 3? If I take the adjoint of gamma I, I'm actually taking the adjoint of beta alpha I. But that, according to the standard rule of taking adjoints, is alpha I dagger, beta dagger. Since alpha I and beta are both Hermitian, this is equal to alpha I beta. But that is not the same as the matrix that you started out with. It's actually negative of beta alpha I. So it's actually negative of gamma I. So gamma I's are anti-Hermitian. Now, there's one compact way of writing this. Once again, we see gamma 0 and gamma I's behave slightly differently. But you can write gamma I dagger, which is minus gamma I, also as gamma 0, gamma I, gamma 0. Remember, gamma 0 anti-commutes with gamma I. So you can write gamma 0, gamma I, gamma 0 as minus gamma I, gamma 0 whole square, which is of course just minus gamma I. But gamma 0 dagger is gamma 0, which also obviously can be written down as gamma 0, gamma 0, gamma 0. So we can put both of these adjoint relations together and write down a single one, which is gamma mu's dagger, where mu could be either 0, 1, 2 or 3, as simply gamma 0, gamma mu, gamma 0. This is going to be very handy in later lectures. To gain some familiarity with these new Dirac matrices, let me repeat a calculation that I did in the last lecture. Strictly speaking, this is not a repeat of that calculation. In the last lecture, what we did was to demand that Dirac's proposed first order equation has to imply the Klein-Gordon equation, because after all, the Klein-Gordon equation is just an embodiment of the energy-momentum relationship in special relativity. Right now what I'm going to do is try to show that the Dirac equation implies the Klein-Gordon equation. There, what we had done was use this demand to figure out conditions on the beta and the alpha matrices. Now that we have recast our equation in the language of the Dirac gamma matrices, and have found out what those conditions tell us about the gamma matrices behavior, we are going to use this to check that the Dirac actually implies the Klein-Gordon equation. For this, what we need to do is first write the Dirac equation in the form of an operator acting on the wave function. Remember, once again, here the wave function is a 4x1 column matrix, and the operator really is a 4x4 matrix valued operator. IH cross gamma mu del mu minus MC I4. Note that because of the presence of the gamma mu, the first term IH cross gamma mu del mu is a matrix valued operator. So second term also has to be a matrix in order to be subtracted from it. And so we don't write it as a number MC, but rather as a matrix MC times the 4x4 identity. Now in order to get from here to the Klein-Gordon equation, what we have to do is square this in some sense. In other words, just apply this operator IH cross gamma mu del mu minus MC I4 twice on psi. Note that the operator in the bracket here is a sum of two terms. The second term is just a number times the identity matrix, so it definitely commutes with the first term. So opening out the square here will obey the standard algebraic rule of a square plus twice ab plus b square. And you don't have to worry about the fact that the cross term is really AB plus BA and not 2AB. So opening this out gives us three terms. The last one is the easiest to understand, is just m square c square times the 4x4 identity acting on psi. And the middle term is simply the twice AB term, twice I h cross gamma mu del mu times MC psi. The MC can of course move out of the derivative and also across the matrices gamma mu because they are just numbers. The very first term is IH cross whole square times the operator gamma mu del mu acting twice on psi, and in order to write it down, what we have done is written this as gamma mu del mu, gamma nu del nu acting on psi. Note that because the mu is a dummy index, I have to change it when I write it again so that I do not confuse the two dummy indices of summation or the two terms. Now let me quickly take a look at the middle term and remind you that according to the Dirac equation, IH cross gamma mu del mu psi is MC psi. So here, if you look at the IH cross gamma mu del mu psi combination, that is being multiplied by twice MC. So it should be easy to understand that this middle term is actually minus 2m square c square psi, and putting all this together, what we end up with is this equation, gamma mu gamma nu del mu psi plus m square c square by h cross square psi equals 0. What we have done to achieve that is we have divided through by h cross square. This is now very similar to the Klein-Gordon equation, but what we now need to do is massage the first term gamma nu del nu and try to see whether we can get the D'Alembert operator out of it. Note that gamma nu del nu, this particular combination is a sum over both mu and nu are therefore dummy indices, so they can be relabeled to anything that you want. In particular, you could actually interchange mu and nu. That is, call what you were calling mu earlier nu and calling nu earlier mu. So this becomes gamma mu del mu. But note that the partial derivatives commute. So you can write del mu as del mu del nu. So overall you end up with two different expressions which are equal. Gamma nu del nu is the same as gamma mu del nu. But then, if two things are equal, then they are equal to half of their sum. Using that, we see that both of these expressions are really equal to half of the anti-commutator of gamma mu and gamma nu times del mu. The anti-commutator of gamma nu, which is and this of course is the standard property which the Dirac gamma matrices have, is twice eta mu nu times the 4x4 identity. So putting them all together, you end up with eta mu nu del nu, and that is simply del upper nu del lower nu. Remember, the eta with upper indices raises indices, and this is nothing but our familiar D'Alembert operator. If you are unfamiliar with this particular way of writing the D'Alembert operator, all I would do is insist that you try expanding this out. Remember, del lower nu's are the derivatives with respect to ct, x0, x1, x2, x3. Del upper nu's are actually the same, but with the spatial terms having an extra minus sign. So this del upper nu, del lower nu combination, which after all is a contraction, a sum over nu is being done here, is simply 1 by c square del 2 del t2 minus del x square minus del y square minus del z square, our familiar D'Alembert operator. So putting all this together, realizing that gamma nu del nu is a D'Alembert operator, tells us that the Dirac operator acting twice on psi equals 0 is essentially the same equation as the Klein-Gordon equation, box plus m square c square over h cross square acting on psi is 0. Note that this is not a new or unexpected result. After all, we had used the fact that the Dirac equation must imply the Klein-Gordon equation to find out conditions on the matrices beta and alpha. which actually has been translated to this anti-commutation relation on the gammas. I would, however, urge you to think carefully about what we have done here, because the kind of calculation that is being done here will be repeated over and over again whenever we use the Dirac equation and try to find out its properties. But now let us move on to the question that we were really asking. What about the covariance of the Dirac equation? We have made the Dirac equation look more covariant now, but that, as I have said, is no guarantee that it's really covariant. What do we really need to make the claim that the Dirac equation is covariant? That is the following. We start with the Dirac equation written down for observer O, IH cross gamma mu del mu psi minus MC psi equals 0. Now what we are going to claim is that this must imply, in fact it must be equivalent to this statement for O prime. IH cross gamma prime mu del prime mu psi prime minus MC psi prime equals 0. Now, because we have to demand that the Klein-Gordon equation stays equally valid in both frames, remember that is the embodiment of the energy-momentum relationship. So any relativistic equation has to imply that the gamma prime mu's must satisfy the same anti-commutation relation as the gammas did. So gamma prime mu would be 0 for mu not equal to mu, but in general you would be able to write this down as this equal to twice eta mu nu I4. Now what I am going to say next has a proof which is pretty straightforward, but it is not a short proof at all. So for the sake of brevity, I am going to skip it here. It is an interesting proof though, so maybe in a later lecture I will come back to this. But what I am referring to is this. We can show that we can always find the unitary transformation which connects gamma and gamma prime if both of them obey the same Dirac condition. So you should be able to find some unitary matrix U such that gamma prime mu is U dagger gamma mu U. This is guaranteed by the fact that gammas and gamma primes obey the same anti-commutation relations, namely the Dirac conditions. Using this result, we can rewrite the equation as observed by O prime in the following form. IH cross U dagger gamma mu U, that's gamma prime mu, del prime mu psi prime minus MC psi prime equals 0. Now if I multiply this equation by U on the left, the U and the U dagger will cancel each other out in the first term, and you will be left with the following equation. IH cross gamma mu del prime mu of U psi prime. Remember, U is independent of space and time coordinates, so it can travel inside the derivative, minus MC times U psi prime equal to 0. Note that if we call U psi prime the wave function instead of psi prime, which is nothing other than a change of picture that we are used to in quantum mechanics, we will end up with the equation IH cross gamma mu del prime mu psi prime minus MC psi prime equals 0. So the transformed equation that will be observed by O prime will have exactly the same form with the same gamma matrices as the original equation as observed by O. The question is, what kind of relationship should psi prime have with psi? In other words, what is the transformation rule which allows us to calculate the new wave function psi prime in terms of the old wave function psi? Now, because the Dirac equation is inherently linear, we would look for a linear transformation to achieve this task. We would want psi prime of x prime, which is of course the same as psi prime of lambda x, lambda being the Lorentz transformation which acts on x to give you x prime, to be related to psi of x by some linear transformation, or in the matrix language by some 4x4 matrix acting on psi of x. This 4x4 matrix, which we are calling S, must of course depend on lambda, the Lorentz transformation which relates the two observers. Of course, this equation is invertible and psi of x works out to be S inverse lambda psi prime of lambda x. Note that you can get back x from lambda x, the new coordinates, by applying the inverse Lorentz transformation. So you could just as well say that this has to be S of lambda inverse acting on psi prime lambda x. And relating the two, we end up with this rather important result, that this function, which maps a Lorentz transformation to a 4x4 matrix, must obey this following condition, that S of lambda inverse must be S inverse lambda. So the question of course is, exactly what is this S for a given Lorentz transformation lambda? To figure this out, we plug in psi prime equal to S lambda in the transformed or the O prime frames Dirac equation, IH cross gamma mu del prime mu psi prime minus MC psi prime equals 0. Here we plug in psi prime equals S psi, but also note that the new derivative del prime mu is related to the old derivatives del nu by lambda lower mu upper nu del nu. Notice that the lambda lower mu upper nu are actually covector transformation coefficients. In a matrix language, they are the mu nueth elements of lambda transpose inverse, or simply speaking, they are just the coefficients del x nu del x prime mu. Plugging all this in, the equation becomes IH cross gamma mu lambda lower mu upper nu del nu of S psi minus MC S psi equals 0, and multiplying both sides of this equation by S inverse, which exists as we saw a while ago, because S inverse lambda is S of lambda inverse, gives you the relationship IH cross S inverse gamma mu S lambda lower mu upper nu del nu psi minus MC psi equals 0. Note that all I have done is I have moved the S outside the derivative for the simple reason that S is a matrix which is a constant, is independent of space and time variables. So, the transformed equation is IH cross S inverse gamma mu S lambda lower mu upper nu del nu psi minus MC psi equals 0, whereas the original equation, the equation in the original frame, unprimed frame O, is IH cross gamma nu del nu psi minus MC psi equals 0. Now, covariance would demand that these two must be the same equation, and therefore, what you must have is the following. For a given lambda, S of lambda inverse gamma mu S of lambda, lambda lower mu upper nu has to be equal to gamma nu. This equation may look a bit more familiar if we were to move the lambda mu nu from the left to the right by using the fact that these are actually the inverse transpose matrices coefficients. This is a very standard trick which you can play here, and that will give you S inverse lambda gamma mu S of lambda is lambda upper mu lower nu. These are of course the coordinate transformation coefficients or the vector component transformation coefficients times gamma nu. Of course, when I say times gamma nu, I mean there is a sum over all nu. So in a way, this particular kind of transformation, this is of course a similarity transformation induced on the gamma mu's, each one of them, and the right hand side seems to imply that the gammas actually combine the same way vector components do. So in a sense, the gamma mu's are strongly related to vector components, although, as we all realize, these gamma mu's are not numbers, these are matrices. So our job now is to find out for any given lambda a 4x4 matrix S of lambda which will satisfy this particular relationship. This does seem like a rather tall order, After all, there are infinitely many Lorentz transformations possible. And what this is asking for is for each such Lorentz transformation, we find a corresponding 4x4 matrix which obeys this equation. Now, what makes this task at all feasible is the fact that we can build up an arbitrary transformation between two inertial observers using many small steps. Strictly speaking, what you see written on the screen right now is not perfectly true. Technically, a Lorentz transformation is any linear transformation of coordinates which leaves the interval x0 square minus x1 square minus x2 square minus x3 square invariant. So among such transformations, there could be something like keep the time the same, x0 does not change, but just change the sign of x1, x2 and x3. This is of course nothing other than the parity operation. You could also think of a time reversal operation where x0 changes sign and x1, x2, x3 stays the same. These will also keep the interval invariant, so technically speaking, they are also Lorentz transformations. And such transformations, in one go the time direction reverses, or in one go the left, right, up and down, all these reverse, the parity operation. These cannot be done in small pieces. This has to be done in one go. However, when we say Lorentz transformation for the time being, we essentially mean transformations which connect one inertial observer to another inertial observer who is moving with respect to that first one and maybe also rotated with respect to the first one. And since you can think of a sequence of intermediate inertial observers, each moving very slowly with respect to the previous one, between our original observer and the final one, we can build up such Lorentz transformations with many small steps. We will soon see how this building up process works, but for the time being, let us take a look at infinitesimal Lorentz transformations, that is, transformations which differ from the identity by very tiny amounts. For a particular infinitesimal Lorentz transformation, the matrix lambda will differ from the matrix of doing nothing, the identity, by only an infinitesimally small matrix. So lambda will be I4 plus omega, where omega is a 4x4 matrix whose entries are all infinitesimally small. Or in terms of components, lambda upper mu lower nu will be delta mu nu plus omega mu nu, where omega mu nu are infinitesimally small. Of course, this could have additional terms of order omega square and above, but because omega mu nu are infinitesimal, the higher order terms are of course negligible. Now, how many such parameters omega mu nu are there for a given infinitesimal transformation? On first glance, it looks like there are 16 such numbers. After all, mu takes 4 values, 0 to 3, so does nu. So there are 16 possible components here. However, we will soon see that that is not the case, because any arbitrary 4x4 matrix cannot qualify as a Lorentz transformation matrix. A Lorentz transformation matrix must obey eta lower mu nu, lambda mu rho, lambda nu sigma is equal to eta rho sigma. This, after all, is nothing but the statement that the interval is invariant, and if we use our infinitesimal matrix components in this relationship, we get eta mu nu times delta mu rho plus omega mu rho, that's of course lambda mu rho, times delta nu sigma plus omega nu sigma must be eta rho sigma. Now, if we multiply out the brackets here, we will get 4 terms, but of which the last one will have 2 omegas that will be higher order or quadratic order in omega, and we can safely ignore that. Among the other terms, term independent of omega happens to be eta mu nu delta mu rho, delta nu sigma, and by the magic of the delta symbol, this summation simply replaces the mu everywhere by a rho and the nu everywhere by a sigma, so you are left with eta rho sigma as the first term on the left hand side. On the other hand, let us now look at terms with a single omega. For example, you could have eta mu nu omega mu rho delta nu sigma. What the delta nu sigma does is changes this nu here to a sigma. So what you get is eta mu sigma omega mu rho, and the eta mu sigma lowers this mu, changing it into a sigma. So this becomes omega sigma rho. We can do a very similar thing with the other term which has a single omega, namely eta mu nu delta mu rho omega nu sigma. And the upshot of all this is the left hand side becomes eta rho sigma plus omega sigma rho plus omega rho sigma, and the right hand side of course is eta rho sigma. So the two eta rho sigmas cancel out and you are left with omega sigma rho plus omega rho sigma equals 0, or omega rho sigma is minus omega sigma rho. So this leaves us with an antisymmetry condition on the omegas, and immediately this tells us that the four diagonal components omega 0, 0, omega 1, 1, omega 2, 2, omega 3, 3 must vanish. And in addition, if you know omega 0, 1, omega 0, 2, omega 0, 3, omega 1, 2, omega 2, 3, omega 3, 1, then you actually know the other 6 terms as well. That's the antisymmetry for you. And this tells us that you have only 6 independent parameters omega here. That actually is consistent with our picture of general Lorentz transformations. After all, if you count all the Lorentz transformations, there are 3 independent rotations. Remember, rotations are Lorentz transformations because they definitely keep the interval invariant, and 3 boosts. So 6 independent transformations in all, and hence the 6 parameters that you get here is perfectly consistent with that. Having identified parameters omega rho sigma, which parametrizes an infinitesimal Lorentz transformation, let us now turn to the question of the form which the matrix S acting on psi takes for such an infinitesimal Lorentz transformation I4 plus omega. This I4 plus omega is our Lorentz transformation, the infinitesimal one. Notice that when omega is 0, the Lorentz transformation simply is the identity, which means you are not really changing from one observer to another at all. And the corresponding S matrix would tell us what happens to our Dirac column vector psi when you do nothing at all. Of course, the answer is nothing should happen to psi in such a case. So the corresponding matrix which acts on the 4-dimensional column vector psi must be the 4x4 identity matrix. On the other hand, when we deviate infinitesimally slightly from the identity matrix, in the sense that we have an infinitesimal transformation lambda, and these omegas are infinitesimally small but non-zero, we would expect S to also deviate from its 0 omega value, I4, by an infinitesimally small amount, and this infinitesimally small amount has been written down in this following form: minus I by 4 omega mu nu sigma mu nu, where the sum of course is over mu and nu. So we are writing down only the part which is linear in omega here. Of course, there could be higher order terms, but for an infinitesimally small omega, those higher order terms would be negligibly small. Now let us examine this term here a bit more closely. The factor minus I by 4 in front has been put in there for later convenience. The omega mu nu's here, they are actually numbers. This is something which is very important to realize, that omega mu nu's are elements of the omega matrix, but they are themselves just numbers. However, S itself is a 4x4 matrix, so this whole term here must be a 4x4 matrix, and that tells us that each of the sigma mu nu's must be 4x4 matrices. So the mu and nu indices here do not talk about components of a matrix, they rather label the matrix. So sigma 01 is one matrix, sigma 02 is another matrix, and so on. Now from the bunch of matrices sigma mu nu, you can actually create two new branches. Let's call them alpha mu nu, which is half of sigma mu nu plus sigma nu mu, and sigma bar mu nu, which is the same thing but with a minus sign in between. Of course, if the labeling had been such that sigma mu nu were already symmetric in mu and nu, that is sigma 01 were the same as sigma 10 and so on, then sigma bar mu nu would have been 0. If on the other hand the labeling had been antisymmetric, then alpha mu nu would have been 0 and sigma bar mu nu would have been the same as sigma mu nu. Now notice that this omega mu nu sigma mu nu combination involves an antisymmetric omega mu nu. And in terms of this alpha and sigma bar, this would simply be alpha mu nu plus sigma bar mu nu. But note that I can interchange the two indices. I can write this equally well as omega nu mu alpha nu mu plus sigma bar nu mu. This is just interchanging the labeling here, changing the dummy indices nu and mu with each other. But now you would realize that the first term would have to vanish simply because omega mu nu and omega nu mu are negatives of each other. Alpha mu nu and alpha nu mu are the same. So this combination would be negative of itself, so it would have to vanish. So out of these 4x4 matrices, only the sigma bar mu nu, the part which is antisymmetric in the indices mu and nu, would actually survive. Because of this, we start out by the demand that the sigma mu nu's are chosen in such a way that sigma mu nu is minus sigma nu mu. You already have antisymmetry built in. Note that we are not claiming that the sigma matrices themselves, these matrices sigma 1 ij's, note that we are not claiming that these matrices sigma mu nu themselves are antisymmetric. We are just saying that the labeling is antisymmetric here. So what we have are 6 independent 4x4 matrices sigma mu nu's. Sigma 00, sigma 11, etc. must vanish, and sigma 01 would tell you what sigma 10 is, and so on. Our job now is to find out these sigma matrices explicitly. And for that, we will have to fall back upon our basic demand that S inverse lambda gamma mu S lambda has to be lambda mu nu gamma nu. Of course, for this we need to know the inverse of this particular S matrix for the infinitesimal transformation, but that's actually pretty easy. S inverse of I plus omega has to be the S corresponding to the inverse Lorentz transformation, and it is easy to establish that the inverse Lorentz transformation corresponds to just changing the sign of omega. If you want to check this out, just multiply out the matrices I plus omega with I minus omega. You are going to get I up to order omega. Remember, the expression for lambda that we are using, the lambda matrix, is accurate only up to first order in omega. So the fact that I minus omega multiplied by I plus omega in whichever order gives you I up to first order in omega is proof that I minus omega is the inverse of I plus omega at this stage. Now S of I minus omega, the inverse of S of I plus omega, has exactly the same expression as s of I plus omega itself, except that the omegas all change sign. So what you are left with is up to order omega, the expression 4 by 4 identity, plus I by 4 omega mu nu sigma mu nu. We are now going to use these expressions, plug them into our basic defining rule about how gamma mu changes under the similarity transformation, and try to figure out basic defining properties of the sigma mu nu matrices using that. So just to quickly repeat, what we are doing is we are using S inverse lambda gamma mu S lambda equals lambda mu nu gamma nu, in which we are using an infinitesimal Lorentz transformation where lambda mu nu is given by delta mu nu plus omega mu nu, and we are using the corresponding expressions for S of lambda and S inverse lambda, which have been written here only up to first order. All these expressions have been written to first order in omega. So if we just plug this into our expression, we get I4 plus small I by 4 omega alpha beta sigma alpha beta gamma mu I4 minus I by 4 omega alpha beta sigma alpha beta equals delta mu nu plus omega mu nu gamma nu. Now you can multiply out the left hand side and you are going to get 4 terms, obviously, of which the last one will involve 2 omegas. That's a quadratic order term which we simply have to drop from this. I might have said before that this quadratic order term is being dropped because it's negligible, but strictly speaking, what I really should have said is that since all our calculations are being done up to order omega, any term of the order omega squared is anyway to be dropped, because there would have been other terms of order omega square which would have contributed, which we haven't taken into account. Anyway, from the other 3 terms, it's obvious that one of the terms is just identity times gamma mu times the identity, which is gamma mu itself. And that cancels with the gamma mu you also get on the right hand side from delta mu nu gamma nu. The other 2 terms involving one power of omega is easily seen to be I by 4 omega alpha beta times sigma alpha beta gamma mu minus gamma mu sigma alpha beta. So what you have is a commutator between the 4 by 4 matrices sigma alpha beta and gamma mu sitting here. So it is now easy to see that the commutator of sigma alpha beta and gamma mu can be written in terms of the gamma betas. In particular, we have I by 4 omega alpha beta times the commutator of sigma alpha beta with gamma mu equals omega mu nu gamma nu, which I have deliberately written as omega mu beta gamma beta. Note once again that nu is a dummy index which can be changed at will. I have changed it to beta simply in order to try to match the omega on the other side. Of course, on the other side you have omega alpha beta with both lower indices, whereas you have omega mu beta here with mu an upper index. But that can be easily handled. You could use eta mu alpha, the upper index eta mu alpha, to raise the index alpha and make it into mu. So the commutator after contraction with I by 4 times omega alpha beta is the same as omega alpha beta eta mu alpha gamma beta. That does not mean, however, that we can just equate the 2 sides by dropping off the omega alpha betas. We have to remember that omega alpha beta is antisymmetric in alpha and beta. So anything which is symmetric in alpha and beta contracted with that vanishes without trace. So the only things we can really compare are the antisymmetric terms together. Now, since sigma alpha beta is already antisymmetric in alpha and beta, the commutator is also antisymmetric in alpha and beta. So there are no problems with the left hand side. The right hand side, on the other hand, as is written, is not antisymmetric in alpha and beta. But you can immediately write this by switching the indices omega beta alpha eta mu beta gamma alpha, and using the fact that omega beta alpha is minus omega alpha beta, you can rewrite the right hand side as half of their sum. So omega alpha beta into half eta mu alpha gamma beta minus eta mu beta gamma alpha And now you can directly compare the two sides and rewrite the commutator. I've just changed the sign a bit to make the I come out in the numerator on the right hand side. So you have the commutator gamma mu with sigma alpha beta is twice I times eta mu alpha gamma beta minus eta mu beta gamma alpha. At this stage, let us pause and take stock of what we have done. What we have achieved so far is the following. We have shown that the Dirac equation can be covariant under Lorentz transformations provided there exists for every lambda a Lorentz transformation, a matrix S of lambda which will act on the Dirac's wave function, the 4x1 column vector. We had found out the condition which this S must obey, namely S inverse lambda gamma mu S lambda must be lambda mu nu gamma nu. So the question really is, do such S's exist? And we had now shown that at least for infinitesimal transformations, such an S would exist if you can find matrices sigma alpha beta, 6 independent such matrices, which obey this particular commutation relation. Gamma mu's commutator with sigma alpha beta is twice I eta mu alpha gamma beta minus eta mu beta gamma alpha. So all we need to do right now is either prove that such sigma matrices exist, or even better, find out explicit forms for such sigma matrices. If we manage to do that, then we show that at least for infinitesimal Lorentz transformations, we can have a way of transforming the Dirac column vectors so that the Dirac equation stays covariant. And since we can build up finite Lorentz transformations using infinitesimal ones, that guarantees that Lorentz covariance will be there for the Dirac equation. However, we still have one more step to go. We have to show that 6 independent matrices sigma alpha beta do exist which obey this particular commutation relation. And that is what we are going to do now. Since the gamma matrices are all we have at this stage, it seems natural that we will try to build up the sigma alpha beta matrices out of the gamma matrices. There is one catch though. This one is a commutator relation, whereas the defining properties for the gamma matrices all involve anti-commutators. However, there is a very nice connection between commutators of products of operators with anti-commutators. Let me just remind you what that is. If you take the product BC and try to find its commutator with the operator or the matrix A, what you get is, of course, ABC minus BCA, the terms written in orange here. But you can always supply two additional terms plus BAC and minus BAC, so that the first two terms together give you AB plus BA times C, and the final two terms give you minus B times AC plus CA. So, the commutator of the product BC with A is given by the anti-commutator of A and B times C minus B times the anti-commutator of A and C. Given the fact that the eta mu alpha times the identity is related to the anti-commutator of gamma mu and gamma alpha, it should be a rather obvious thing to try the product gamma alpha gamma beta here. So let's try the commutator of gamma mu with gamma alpha gamma beta. According to the formula that we had just derived, is the anti-commutator of gamma mu with gamma alpha times gamma beta minus gamma alpha times the anti-commutator of gamma mu times gamma beta. But these anti-commutators are, of course, the well-known Dirac anti-commutators, and that gives us twice eta mu alpha gamma beta minus twice eta mu beta gamma alpha, which looks almost exactly like what we really need. However, there is a catch. Despite the fact that the eta mu alpha gamma beta minus eta mu beta gamma alpha is, apart from a factor, exactly what we need for our commutation relation, we simply cannot claim gamma alpha gamma beta, the product, to be sigma alpha beta. After all, sigma alpha beta is antisymmetric in alpha and beta. But that is easily remedied. Instead of taking gamma alpha gamma beta, the product, all you have to do is take the commutator of gamma alpha with gamma beta. It is very easy to see that the additional term minus gamma beta gamma alpha would actually give you exactly the same result. So the commutator of gamma mu with the commutator of gamma alpha gamma beta is 4 times eta mu alpha gamma beta minus eta mu beta gamma alpha. Now this is exactly what we need, except for a factor. And taking that factor into account, it is obvious that we can identify the matrix sigma alpha beta to be the commutator of gamma alpha with gamma beta with an additional factor of I by 2, which of course after multiplication by the 4 manages to give you the necessary 2i that you need in the commutator between gamma mu and sigma alpha beta. And written in terms of this particular form for sigma alpha beta, our formula for the transformation matrix for the Dirac wave function under an infinitesimal Lorentz transformation is given by I4 plus 1/8 omega alpha beta times the commutator of gamma alpha with gamma beta. Thus, we have managed to achieve our goal, which was to show that under a Lorentz transformation, at least under an infinitesimal Lorentz transformation, we can figure out ways of transforming the Dirac wave function so that the Dirac equation stays covariant. We are going to expound on this further in the next lecture. We are going to discuss how to build up finite transformations from these infinitesimal ones. We are going to use the transformation rules to explore some properties of the Dirac solutions, as well as to show, for example, that the Dirac particle actually is a particle which has spin 1/2 or spin projection h cross over 2. But let me just end today's lecture by showing you some explicit forms for these sigma alpha beta matrices. We are going to use the only representation that we have seen so far, the one in which the beta matrix or the gamma 0 matrix is diagonal, the so-called Dirac representation. And in that representation, let us try to see what form our independent sigma alpha betas take. There are two distinct kinds of sigma alpha betas, as it turns out. One in which one of the indices happens to be 0. So let's consider sigma 0 I, where I runs from 1 to 3. Of course, sigma I0 will simply be the negative of this. From our defining relation, which we have just derived, it is going to be I by 2 times the commutator of gamma 0 with gamma I. And if we use gamma 0 and gamma I as given in the Dirac representation, it is very easy to see that gamma 0 gamma I and gamma I gamma 0 are both very similar in form. 0 sigma I 0 for one and 0 minus sigma I 0 for the other. So that the commutator, after you multiply it by I by 2, simply becomes I times a block diagonal matrix with sigma I sitting on the two diagonal positions. So you have sigma I 0, 0 sigma I. Reminding you once again that these are actually 4 by 4 matrices which have been written in the form of 2 by 2 blocks. On the other hand, if both the indices involved are spatial indices, that is sigma ij, where I and j runs from 1 to 3, it is very easy to do the same calculation and to show that gamma I gamma j is minus sigma I sigma j 0, 0 minus sigma I sigma j. So that the commutator of gamma I with gamma j will essentially involve commutators of sigma I with sigma j on the diagonal blocks, and this will immediately give rise to a rather familiar form. The commutator of sigma I with sigma j is of course our familiar result, twice I epsilon I j k sigma k. And using the I by 2 in front, we see that the sigma ij's are almost like the spin half generators of rotation. This similarity actually is not accidental. We will see in the next lecture that this will tell us that the way in which the Dirac particle responds to a rotation of coordinates is exactly the same as for a spin half particle, which is what helps us to identify this particle as something which has spin 1/2, which makes it a natural candidate to describe particles like the electron. But more on that in the next lecture. Goodbye for now.